Good evening, children.
Good evening, ma'am.
Good evening, children.
Good evening, ma'am.
Good evening, children.
Good evening, ma'am.
Good evening.
Good evening, ma'am.
Good evening, children. Good evening.
Good evening.
Good evening. Okay, so we have done quite a few numericals from this chapter, circles. Let's see the theorems involved in this chapter, circles now. So this is the first theorem. The perpendicular from the center of a circle to the chord bisects the chord. The perpendicular from the center of a circle. So we have a circle. And if we draw a perpendicular from the center of a circle to the chord is bisected. It bisects the chord. So see here. Circle, center. Say we have a chord AB. Say we have a chord AB. Circle with center O. AB is a chord of the circle. If you draw a perpendicular from the center to the chord, if you draw a perpendicular, that is, say you draw a perpendicular OM from the center to the chord AB. The chord is bisected. That is, M is the midpoint of AB. AM is equal to MB. The perpendicular from the center to the chord bisects the chord. Circle, center O, chord AB. If you drop a perpendicular from the center, if you drop a perpendicular from the center to the chord, so from the center, if you draw a line perpendicular to the chord, so let's say OM is perpendicular to AB. Let's say OM is perpendicular to OM is drawn perpendicular to AB. Then OM bisects AB. OM bisects AB meaning AB is divided into two equal halves. M being the midpoint of AB. AM is equal to MB. To prove this result, the construction is to join OA, join OA, join OB. So we have two triangles. Let's show that the two triangles are congruent to each other. So you can see here. Angle 1, the triangles are OMA. Triangles are triangle OMA and triangle OMB. So angle 1, this angle 1 is equal to angle 2, 90 degrees. Angle 1 of the first triangle is equal to angle 2 of the second triangle, 90 degrees. Then OA of the first triangle is equal to OB of the second triangle, radii of the circle. OM is equal to OM, common side. OM is equal to OM, common side. See, how do we know that 1 and 2? 1 is equal, 1 and 2 are each 90 degrees. That's given to us in the statement. The perpendicular from the center to a chord bisects the chord. So we are given a perpendicular from the center to the chord. We'll have to prove that the chord is bisected. So we are given that OM is perpendicular to AB. We are given that OM is perpendicular to AB. We need to prove that AM is equal to MB. We are given that OM is perpendicular to AB, the chord AB. So we know that angle 1 is 90, 2 is 90. But we need to prove that AM is equal to MB. The chord is bisected. For which we'll have to show that triangle OMA and triangle OMB are congruent to each other. So here we prove it by using the RHS congruence criterion. You can see here right angle, hypotenuse OA is equal to OB. Hypotenuse are equal in both the triangles. And OM is the common side. SRHS. OM is a common side to the two triangles. So by RHS congruence criterion, the two triangles are congruent. So CPCTC, we have AM is equal to BM. So triangle OMA is congruent to triangle OMB by the RHS rule. CPCTC, we have MA is equal to MB. MA is equal to MB, CPCTC. So if MA is equal to MB, MA is equal to MB. That means M is the midpoint of MA is equal to MB. That means M is the midpoint of AB. That means OM bisects AB. The perpendicular OM bisects AB. Clear, children? So the statement is this one. The perpendicular from the center of a circle to a chord bisects the chord. If you draw a perpendicular from the center of the circle to a chord, it bisects the chord. The perpendicular from the center to a chord bisects the chord. That's a statement. So we are given a chord, let's say AB. Let's call it AB. Given chord AB of a circle with center O and radius R. We're given a chord, we've called it AB. Given chord AB of a circle with center O and radius R. And what else we know? We know that OL is perpendicular to AB. We also know that OL is perpendicular to AB. We are given that OL is perpendicular to AB. What is that we have to prove? We'll have to prove that LA is equal to LB. We'll have to prove that LA is equal to LB. So construction, join OA, join OB. Join OA and OB, that's a construction. We are given a circle with center O and radius R. We are given a chord AB. And we have to draw from the center, we have to draw the perpendicular to the chord. The perpendicular here is called OL. We have to draw the perpendicular from the center to the chord. So all this is given to us. We need to prove that LA is equal to LB. Construction, join OA, join OB. Then show that the two triangles are congruent to each other. So in the two triangles OLA and OLB, angle OLA, this is angle OLA. Angle OLA is equal to angle OLB is equal to 90 degrees. That's given to us. OA is equal to OB, radius, each equal to R. And OL is the common side. So right angle, hypotenuse and common side, S. The two triangles are congruent. OLA is congruent to OLB. So CPCTC, LA is equal to LB, which proves that the chord is bisected at L. Understand, children?
Yes, ma'am.
The perpendicular from the center of a circle to a chord bisects the chord. Circle, chord, from the center, if you drop a perpendicular to the chord, from the center, if you drop a perpendicular to the chord, the perpendicular bisects the chord, cuts the chord into two equal halves. So now let's see the converse of this theorem. If you draw any line from the center of the circle to bisect a chord, then that line is perpendicular to the chord. See, in the theorem we just saw, we are given a circle. The theorem which we just saw, we are given a circle, chord, and we have a perpendicular from the center to the chord. We draw a perpendicular from the center to the chord. We draw a perpendicular from the center to the chord. And the result is the chord is bisected. The chord is bisected. The converse is circle, center O, or we have a chord AB. There is a line from the center. There is a line, not a perpendicular. There's a line drawn from the center to the chord, which bisects the chord. That is AN is equal to LB. There is a line from the center to the chord that bisects the chord, that divides the chord into two equal halves. So if the chord is bisected, you need to prove that the line from the center is perpendicular to the chord. So it's just this, there are two things here. If it is perpendicular, if the line from the center is perpendicular, then the chord is bisected. If the chord is bisected, then the line from the center is the perpendicular. Perpendicular and bisected. These are the keywords. If OL is perpendicular to AB, then if OL is perpendicular to AB, then L is the midpoint of AB. Now here we see that OL is perpendicular to AB. See, here I've marked OL. OL is a line. O is the center of the circle. So OL is a line from the center and it's perpendicular to the chord. So if OL is perpendicular to AB, then L is the midpoint of AB. L is the midpoint of AB. The chord is bisected. The converse is OL is not a perpendicular. OL is a line from the center to the chord, but it bisects the chord. L is the midpoint of AB. L is the midpoint of AB. OL is some line from the center to the chord and it bisects the chord. Then OL should be perpendicular to the chord. That is, if the chord is bisected, if L is the midpoint of AB, then OL is perpendicular to AB. If OL is perpendicular to AB, then L is the midpoint of AB. If L is the midpoint of AB, then OL is perpendicular to AB. So the statement for this one is, if a line from the center to the chord bisects the chord, then the line is perpendicular to the chord. If a line from the center to the chord bisects the chord, if a line from the center to the chord bisects the chord, then the line is perpendicular to the chord. The statement here is the perpendicular from the center to the chord bisects the chord. Here, a line, if you draw a line from the center, if a line from the center to a chord bisects the chord, then the line is perpendicular to the chord. The line drawn through the center of a circle to bisect the chord is perpendicular to the chord. The line drawn through the center of a circle to bisect the chord. It's not a perpendicular. There is a line from the center to the chord and the chord is bisected. It bisects the chord. Then that line should be perpendicular to the chord. So here OM is a line. OM is a line from the center to the chord and it bisects the chord. That is AM is equal to MV. Then that means OM should be perpendicular to AB. OM should be perpendicular to AB. The line drawn through the center of a circle to bisect a chord. From the center of the circle, if there's a line on the chord and the chord is bisected, then that line is perpendicular to the chord. See here. So circle, what are we given? Circle with center O, chord AB. We have, say, OM. We have OM from the center to the chord, which bisects the chord. So we are given AM is equal to MB. We need to prove that OM is perpendicular to AB. We are given that AM is equal to MB. We are given that AM is equal to MB. This line OM from the center to the chord bisects the chord. This line OM from the center to the chord bisects the chord. AM is equal to MB. The chord is bisected. Then that means OM should be perpendicular to AB is what we have to prove. A line from the center to the chord. OM is a line from the center to the chord and it bisects the chord. So we are given that M is the midpoint of AB. M is the midpoint of AB, or in other words, we know that AM is equal to MB. We need to prove that OM is perpendicular to AB. OM is perpendicular to AB. So again, construction, we'll complete the triangles, join OA, join OB, join OA and OB. So now we have two triangles. Let's show that these two triangles are congruent to each other. So OM is equal to OM, common side. OM is equal to OM, common side. AM of this triangle is equal to MB of this triangle, given the chord is bisected, no? So AM of this triangle is equal to MB of this triangle, given. And then OA of one triangle is equal to OB of the other triangle, radii of the same circle. So by SSS congruence criterion, the two triangles are congruent. OM is the common side, AM is equal to MB, and then OA is equal to OB. So by SSS rule, the two triangles are congruent to each other. So CP-CTC will have this angle equal to this angle. This angle is equal to this angle, CP-CTC. So supposing we call it angle 1 and angle 2. Angle 1 is equal to angle 2, CP-CTC. But angle 1 plus 2 is equal to 180. They form a linear pair. 1 is equal to 2, CP-CTC. The two triangles are congruent, so their corresponding angles are equal. But angle 1 plus 2 is equal to 180. Linear pair. So 1 plus 1, 1 and 2 are equal. 1 plus 1 is equal to 180. Twice of angle 1 is equal to 180. Angle 1 is equal to 90 degrees. So angle 1 is equal to 90 degrees means OM is perpendicular to AB. Angle 1, you can also get angle 2 is equal to 90 degrees. Not that you will have to show 1 is 90. Show either 1 or 2 is 90. So when 1 or 2 is 90 degrees, that means OM is perpendicular to AB. OM is perpendicular to AB. So children, the two theorems, the theorem and its converse, they're very, very simple. In one case, we'll see it again. We're given circle with center O. Here also we have chord AB. We're given a chord AB. In the converse also we have a chord AB. In the theorem, we have OM. This is the perpendicular from the center. This is the perpendicular from the center to the chord. OM is the perpendicular from the center to the chord. So if it's given it's a perpendicular, you'll have to prove that it bisects the chord. The perpendicular from the center to the chord, you should prove bisects the chord. So if you're given that OM is perpendicular to AB, if this is given to you, you'll have to prove that AM is equal to MB. The chord is bisected. AM is equal to MB. So here the statement is the perpendicular from the center to the chord, from the center, not from any point in the circle, from the center. The perpendicular from the center to the chord bisects the chord. Bisects the chord is what we have to prove. The converse is if a line is drawn from the center to bisect the chord. Now, OM is a line. OM is a line from the center to the chord and it bisects the chord. OM is a line, not perpendicular. OM is a line from the center to the chord and it bisects the chord. OM is a line from the center to the chord and it bisects the chord. That means we are given that AM is equal to MB. It bisects the chord. AM is equal to MB. This line from the center, OM, which is a line from the center, it bisects the chord. AM is equal to MB. So we have to prove that OM is perpendicular to AB. OM is perpendicular to AB. So see here given OM perpendicular to AB, we prove AM is equal to MB. Here given AM is equal to MB, we prove that OM is perpendicular to AB. So this is the theorem and this is the converse. This is the converse. In both the cases, construction, join OA, join OB. Here also join OA, join OB. Show that here the triangles will be congruent by RHS rule. Here the triangles are congruent by SSS rule. So here you will get CP/CTC, AM is equal to MB directly. So here you will get CP/CTC, angle 1 is because you'll have to prove that OM is perpendicular to AB, right? So you will get angle 1 is equal to angle 2. You'll have to write this. Angle 1 is equal to 2, but 1 plus 2 is equal to 180. So proceeding, you will get angle 1 is equal to 90 degrees, which means OM is perpendicular to AB. Yes, children, please take a screenshot of this one. You may write it later. Take a picture. And this one. So this is what we discussed. So we are given that M, this is the converse. We are given that M is the midpoint of the chord AB. We'll have to prove that OM is perpendicular to AB. We'll have to prove OM is perpendicular to AB. Join OA, join OB. You can see that the triangles are congruent by SSS congruence rule. So CP/CTC, OMA, this angle is equal to OMB. But angle OMA plus OMB is equal to 180. Angle OMA plus angle OMB is equal to 180. They're equal angles and they're supplementary. So working, you get angle OMA is 90 degrees. OMA is equal to 90 degrees, which means OM is perpendicular to AB. Take a screenshot, children. So we say the perpendicular from the center to a chord bisects the chord. First, in the statement, in the theorem, we have the perpendicular from the center. In its converse, we say the line, not perpendicular, the line drawn from the center of a circle. The line drawn from the center of the circle to bisect the chord is perpendicular to the chord. Okay. Next theorem. Equal chords of a circle subtend equal angles at the center. Equal chords of a circle subtend equal angles at the center. Equal chords of a circle. Equal chords of a circle subtend equal angles at the center. So say we have two chords AB and CD. two chords AB and CD, they're equal chords of a circle. So AB is equal to CD. If the chords are equal, the angles they subtend at the center are also equal, is what we have to prove. Equal chords subtend, equal angles at the center. So here we are given that chord AB is equal to chord CD. We'll have to prove that. So let's take the center of the circle O. Now only when you join OA and OB, you can make out the angle subtended by AB at the center. Similarly, only when you join CO and CD, sorry, CO and DO, only when you join CO and DO, you can make out the angle subtended by CD at the center. So these are the angles. This is the angle. Let me just call it 1 and 2. Angle 1 is the angle subtended by chord AB at the center. Angle 2 is the angle subtended by chord CD at the center. If AB is equal to CD, then angle 1 is equal to angle 2 is what we have to prove. If AB is equal to CD, given AB is equal to CD, we'll have to prove that angle 1 is equal to angle 2. Equal chords subtend equal angles at the center. Circle, center O, chord AB, chord CD, they're equal. The two chords are equal. The two chords are equal. It's given equal chords. It's given that the chords are equal. AB is equal to CD. Now, what is the angle made by chord AB at the center? Join A to O, B to O. This is the angle made by chord AB at the center. What is the angle? Which is the angle made by chord CD at the center? Join C to O, D to O. This is the angle made or subtended by chord CD at the center. If AB is equal to CD, we need to prove that angle 1 is equal to angle 2. So again, prove that the two triangles are congruent to each other. CP/CTC, you will get angle 1 is equal to angle 2. So in these two triangles, we have AB of this triangle equal to CD of this triangle. Then correct.
OA
Correct.
and OC are equal.
Very good.
OB and OD are equal, ma'am.
Very good. So what is the rule?
SSS, ma'am.
SSS rule, the triangles are congruent. CP/CTC 1 is equal to 2. Very good. Yeah. AB is equal to CD given. OA is equal to OC, radii of the circle. Similarly, OB is equal to OD, radii of the circle. SSS rule, the triangles are congruent. CP/CTC 1 is equal to 2. Equal chords subtend equal angles at the center. Now the converse of the theorem. Chords that subtend equal angles at the center are equal. Chords that subtend, see, not equal chords. Chords that subtend equal angles at the center are equal. So here in this case, we have two chords. We are not given that they're equal, but they make equal angles at the center. They make equal angles at the center. What is given here, children? What is given here?
AB is equal to CD, ma'am.
Wrong. In the converse. What is given in the converse? Yeah?
1 is equal to angle.
Angle 1 is equal to angle 2. Angle 1 is equal to angle 2 is given to us. What is that we have to prove?
AB is equal to CD.
AB is equal to CD. If angle 1 is equal to angle 2, then AB is equal to CD. Chords that subtend equal angles at the center. If two chords, they make equal angles at the center, then the two chords are equal in length. Angle 1 is subtended by AB at the center. Angle 2 is subtended by CD at the center. If angle 1 is equal to angle 2, then AB is equal to CD. Chords that subtend equal angles at the center are equal. So if angle 1 is equal to angle 2, then AB is equal to CD is what we have to prove. Yes, children. What do we have in the two triangles? In triangle AOB and triangle COD. What is that we can list? OA is equal to OC. OA is equal to OC. Then angle 1 is equal to angle 2.
OB is equal to OD, ma'am.
Yeah. So what is the congruence rule?
SAS, ma'am.
SAS rule. SAS rule, the two triangles are congruent. CPCTC, AB is equal to CD. So the theorem is circle, center O, AB and CD are equal chords. Equal chords. If AB is equal to CD, then the angle made by AB at the center is equal to the angle made by CD at the center. If AB is equal to CD, then angle 1 is equal to angle 2. Equal chords subtend equal angles at the center. The converse is chords that subtend equal angles at the center are equal. So if angle 1 is equal to angle 2, then AB is equal to CD. So if AB is equal to CD, if the chords are equal, then the angles are equal. Then angle 1 is equal to angle 2. If angle 1 is equal to angle 2, if the angles subtended by the chords at the center are equal, then the chords are equal. Then AB is equal to CD. Take a screenshot, children. This is the converse. If the angles subtended by two chords at the center of a circle are equal, then the chords are equal. So here we are just given two chords, AB and CD. We are given two chords, AB and CD. It's not given that they are equal, but the angles they subtend at the center are equal. The angles they subtend at the center, they are equal. Then we'll have to prove that the chords are equal. The same thing. The triangles are congruent, so CPCTC, you have AB is equal to CD. Equal chords of a circle are equidistant from the center. Equal chords of a circle are equidistant from the center. So see, circle, this is the next theorem, circle, center O. We have two equal chords. Okay, we have two equal chords. Equal chords meaning chords are equal in length. We have two equal chords. AB and CD are two equal chords. Okay. So say ABCD both are equal to say 6 centimeters. They're equal chords. Equal chords are equidistant from the center. This is the center. Distance is always perpendicular distance. When we say distance, it's always perpendicular distance. Now, so which is the, we'll have to show the perpendicular distance of AB from the center. So see here, let's draw the perpendicular. So this one, this is the perpendicular distance of AB from the center. Let's call it OM. OM is the perpendicular distance of AB from the center. OM is the perpendicular distance of AB from the center. ON is the perpendicular distance of CD from the center. If AB is equal to CD, then OM is equal to ON. If the two chords are equal, then their distances from the center are also equal. Equal chords of a circle are equidistant from the center. So if OM is say like 3 centimeters, then ON is also 3 centimeters. If AB is equal to CD, then the distance of AB from the center is equal to the distance of CD from the center. So if this distance is 3 centimeters, this distance is also 3 centimeters. Why? Because AB is equal to CD. Distance is always perpendicular distance. Distance is always perpendicular distance. Two chords. The two chords are equal in length. The two chords are equal in length. Chord AB is equal to chord CD. This is the perpendicular distance of chord AB from the center. This is the perpendicular distance of chord CD from the center. Let's call it P and Q. If the length of the chord AB is equal to the length of the chord CD, then this distance OP is equal to this distance OQ. Equal chords of a circle are equidistant from the center. How do we prove this? So let's complete the triangles. Join OA, join OC. Let me just draw a bigger figure. Two chords, their perpendicular distances from the center. Okay, so let's call it AB and CD, and the perpendicular distances say M and N, center O. This is what we have. We are given that AB is equal to CD. We have to prove that. What do we have to prove, children?
OM is equal to ON, ma'am.
Very good. We'll have to prove that OM, the distance OM is equal to the distance ON. So construction, join OA so that we get a triangle, and join OC. Construction, join OA and OC. Construction, join OA, OC. Now we'll have to prove that these two triangles are congruent to each other. Tell me, children, how do we show that these two triangles are congruent to each other? Yes, Nikita.
Ma'am, OA is equal to OC, ma'am, radius of the circle.
Okay, OA is equal to OC. Then
And AM is equal to CN.
A
M is equal to CN, ma'am, by the converse of the. theorem.
Explain that. How do you get AM is equal to CN?
Ma'am, in the previous theorem, we saw that in the converse of the theorem, if the center, if AB is equal to CD, then the line drawn from the center bisects the chord, ma'am. So it's AM is equal to BN. So
Correct.
it will be equal, no, ma'am.
Perfect. Yes. So AB is equal to CD. Correct. AB is equal to CD because it's given. Chords are equal. Half of AB will be equal to half of CD. And by the theorem, we know that the perpendicular from the center to the chord bisects the chord. So M is the midpoint of AB, N is the midpoint of CD. Because OM and ON are perpendiculars from the center to the chord, the respective chords are bisected. Perpendicular. OM is perpendicular to AB. So OM bisects AB. ON is perpendicular to CD. So by the theorem, ON bisects CD. The perpendicular from the center to the chord bisects the chord. OM is perpendicular to AB. So OM bisects AB. OM bisects AB. Similarly, ON is perpendicular to CD. So ON bisects a CD. ON bisects CD. So we say half AB is equal to CD. Half of AB is equal to half of CD. Half of AB is AM is equal to half of CD is CN. So this is one information. AM of this triangle is equal to CN of this triangle, correct? Then what else we have, children? AM is equal to CN. Next, we need to list out 3 equalities.
We listed 3 equalities, ma'am. AB is
Yeah, I just want it again. Correct. Yeah, you're right. Just repeat.
yes, ma'am. AB is equal to CD, ma'am, and half of AB is half of CD, so AM is equal to CN.
So AM is equal to CN is the first thing. Okay, then AM of triangle AOM is equal to CN of triangle COM. Then
OB and OD, ma'am. OB and OD.
They are not in picture at all, no, OB and OD. We are talking about the triangles. We are talking about these 2 triangles. They are not in picture at all.
OA is equal to OC, ma'am.
OA is equal to OC. Okay, so this is equal to this. OA is equal to OC. Then one more. Class.
I'm not sure about the next one, ma'am.
Oh, it's right there in the figure. Distance is always perpendicular distance, right? So we know that this is 90 degrees. Angle 1 is equal to angle 2, 90. Class. Yeah, Nivedita. Class, angle 1 is equal to angle 2, 90 degrees. That makes R. OA is equal to OC. Radii of the circle, H. And then AM is equal to CN. S. RHS rule, the 2 triangles are congruent. So CP, CTC, you will have OM is equal to ON. So if AB is equal to CD, then OM is equal to ON. I want one of you to repeat this, not Nivedita, somebody else. Arav, are you there? What is given, children? What do we know about AB and CD? What do we know about AB? What is the theorem? Equal chords are equidistant from the center. Equal chords are equidistant from the center. So we are given that AB and CD are two equal chords. We are given that AB and CD are two equal chords. AB is equal to CD. We need to prove that their distance from the center are also equal. So let's show the distance of chord AB from the center. This is the center O. Distance is always perpendicular distance. Again, distance is always perpendicular distance like this. So OM is perpendicular to AB. OM is the distance of AB from the center. ON is the distance of CD from the center. Then after this you can join AO and CO, or you can join this and join this. Just get two triangles. Show that these two triangles are congruent. CP, CTC, you will get ON is equal to OM. So if AB is equal to CD, then OM is equal to ON. So what you have to list out is angle 1 is equal to angle 2, 90 degrees. OB is equal to OD, radii of the circle. So right angle, hypotenuse is over. Then some side. We're using another theorem here. AB is equal to CD. Half of AB is equal to half of CD. And half of AB is MB. Because we know that the perpendicular from the center to the chord bisects the chord. Since OM is perpendicular to AB, OM is perpendicular to AB, it bisects AB. So half of AB is MB. Similarly, ON is perpendicular to CD, so it bisects CD. Half of CD is ND. MB is equal to ND. This is the third information or third equality. RHS rule, the triangles are congruent. CP, CTC, OM is equal to ON. The converse of this theorem is if we have two chords whose distances from the center are equal. So supposing this is 5 centimeters, this is also 5 centimeters. OM is 5 centimeters, ON is also 5 centimeters. We have two chords which are equidistant from the center. Excuse me. We have two chords that are equidistant from the center. Then the chords are equal in length. That is, if the distance OM is equal to the distance ON, then the chord AB, the length of the chord AB is equal to the length of the chord CD. If OM is equal to ON, if the distance of the OM is the distance of chord AB from the center, ON is the distance of chord CD from the center. If OM is equal to ON, then AB is equal to CD. Chords that are equidistant from the center are equal. So now show that these two triangles are congruent, children. Show that these two triangles are congruent. What have we given here? We are given that OM is equal to ON. We are given that OM is equal to ON. We'll have to prove that AB is equal to CD. We'll have to prove that AB is equal to CD. Chords that are equidistant from the center are equal. The two chords AB and CD, they are equidistant from the center. That is OM is equal to ON. We'll have to prove that AB is equal to CD. Just tell me the information. Tell me the equalities. We'll have to list to show that OMB is congruent to ONC.
Angle OMB is equal to angle ONC, ma'am. They're 90 degrees.
Okay, OMB is equal to ONC. Very good. Next.
And OM is equal to ON, ma'am. It's given, ma'am.
Correct. OM is equal to ON given. Very good. Next.
OB is equal to OC radii of the circle, ma'am.
Very good. OB is equal to OC radius. Yes. So what rule it makes?
And RHS, ma'am.
RHS. RHS.
By
RHS.
CP, AB is equal to CD, ma'am.
No. AB is not a side of the triangle. No, we've taken up. You cannot get AB is equal to CD straight away. What will you get? OMB is congruent to ONC by RHS rule.
Yes.
Yeah, what will you get? CPCTC class. Yes, class CPCTC, what we have?
MP is equal to NC.
Very good. MB is equal to NC. MB is equal to NC, CPCTC.
Okay, ma'am.
Sorry, children. Yes, MB is equal to NC, then? Yeah, MB is equal to NC. Twice of MB will be equal to twice of NC. Doubles of equals are also equal. And since OM is a perpendicular from the center to the chord, it bisects the chord. So twice MB is nothing but AB. And twice NC, again, perpendicular from the center to the chord, perpendicular from the center to the chord, bisects the chord. ON is a perpendicular from the center to the chord, so it bisects the chord. So N is the midpoint of CD. So 2 times NC will be CD. MB is equal to NC, CP, CTC. Doubles of equals are also equal. So twice MB is equal to twice NC. Twice MB is AB and twice NC is CD. Or you can also write MB. After this, you can also write MB as half of AB is equal to, you can write NC as half of CD. What is MB? MB, it's half of AB. What is NC? It's half of CD. MB can be written as, or MB can be substituted with half AB. Because MB is half of AB. NC is half of CD. then half on either side gets cancelled. AB is equal to CD. Yes, children, take a screenshot. Is the converse. This is what we've seen so far. The perpendicular from the center. The perpendicular from the center to a chord bisects the chord. Bisects the chord. The perpendicular from the center to a chord bisects the chord. So, circle, chord, from the center, if you draw a perpendicular, from the center, if you draw a perpendicular to the chord, so if you draw OM perpendicular to the chord AB, if you draw OM perpendicular to the chord AB, then the chord is bisected. AM is equal to MB. The perpendicular from the center to the chord bisects the chord. Converse of this one is a line from the center of the circle if a line, we'll say if a line, I can't complete it otherwise, if a line is drawn, from the center of the circle to bisect, if a line is drawn from the center of the circle to bisect, if a line is drawn from the center of the circle to bisect a chord, if you draw a line, you don't draw a perpendicular, you draw a line. If a line is drawn from the center of the circle to bisect a chord, then the line is perpendicular to the chord. If it is perpendicular, then it bisects the chord. If the chord is bisected, then the line is perpendicular to the chord. So here, this is circle, chord. You draw a line from the center. You draw a line from the center to the chord. You draw OL from the center to the chord. And OL bisects AB. OL bisects AB. OL is just a line from the center. OL is not perpendicular. OL is a line from the center and bisects the chord AB. Then OL is perpendicular to AB. Because OL bisects AB, OL will be perpendicular to AB. If a line is drawn from the center of a circle to bisect a chord, then the line is perpendicular to the chord. So supposing we are given a figure like this. Supposing we are given this is 5 centimeters, this is also 5 centimeters. MA is 5 centimeters, MB is also 5 centimeters. That means you can mark a right angle here. You can mark a right angle here. Because MA is 5, MB is also 5. The chord is bisected. The chord is bisected. MA is equal to MB. The chord is bisected at M. That means OM is perpendicular to AB. Supposing we know that AB is 12 centimeters. We know AB is 12 centimeters. So you can conclude that AM is 6 centimeters and MB is also 6 centimeters. If AB is 12 centimeters, because OM is perpendicular to AB, it bisects AB. So AB is 12, so AM is 6 and MB is 6. Then equal chords are equidistant from the center. Equal chords, circle. If two chords are equal, if these two chords are equal in length, then their distance from the center, distance is always perpendicular distance. If supposing we are given this is 10 centimeters, this chord is 10 centimeters, and this is say like 7 centimeters, this also will be 7. If the two chords are of equal length, then their distance from the center will also be equal. Equal chords are equidistant from the center. Converse, if two chords are equidistant from the center, then the chords are equal. If two chords are equidistant from the center, okay, so this is 3 and this is 3. This is the distance of, you can see this is the distance of this chord from the center, and this is the distance of this chord from the center. The distances are both 3. So that means this chord AB is equal to this chord CD, because their distance from the center are equal. Because OM is equal to ON. OM is equal to ON. AB is equal to CD. Then equal chords subtend equal angles at the center. Equal chords subtend equal angles at the center. If these two chords are equal, then they'll subtend equal angles at the center. This angle is equal to this angle. Equal chords subtend equal angles at the center. If this chord is equal to this chord, then this angle is equal to this angle. Chords that subtend equal angles at the center are equal. Chords that subtend equal angles at the center are equal. Sorry. Yeah, if angle 1 is equal to angle 2, then chord AB, the length of the chord AB is equal to the length of the chord CD. If angle 1 is equal to angle 2, then AB is equal to CD. Chords that subtend equal angles at the center are equal. So the perpendicular from the center to the chord bisects the chord. The perpendicular from the center to the chord bisects the chord. If a line is drawn from the center to bisect the chord, then the line is perpendicular to the chord. Theorem, converse. Equal chords are equidistant from the center. Theorem, converse. Chords that are equidistant from the center are equal. Theorem. Equal chords subtend equal angles at the center. Converse. Chords that subtend equal angles at the center are equal. That we finished the 6 theorems we have in this chapter. All this you can just take a picture, children. This is exercise 10.1, answers to exercise 10.1. Take a screenshot. Fill in the blanks and true or false. Take a screenshot, children. That's all. This exercise 10.1. True or false, and this one. Fill in the blanks. We have discussed all this when we understood the introduction to this chapter. Again, very simple, simply congruency. When do we say that two line segments are congruent, children? When do we say that two line segments are congruent?
And when the radii of the circle, ma'am.
No, when do we say that two line segments are congruent? If I say line segment AB is congruent to line segment CD, that means
They're equal.
And their
Yeah.
chord of equal chord of the circle.
no, it's not about chords here. We're not talking about circles. If line segment AB is congruent to line segment CD, it means they're of the same length. That means the length of AB is equal to the length of CD. Congruence means equal. Congruency, congruent, equal. Line segment AB is equal to line segment CD. Is what is line segment AB is congruent to line segment CD. So two line segments are congruent if they're of the same length. If AB is 10 centimeters and CD is also 10 centimeters, that means AB and CD are congruent to each other.
Okay.
Do you understand, children?
Yes, ma'am.
When are two angles congruent to each other?
And when they are in the same length, ma'am.
No.
When the measures of their angles are equal.
Yeah. So here we have angle AOB. This is angle AOB and this is angle DCF. If we say that angle AOB is congruent to angle DCF, that means they're of the same measure. This is 45 degrees, this is also 45 degrees. Two angles are said to be congruent if their magnitudes are the same or if they're of the same magnitude. Two angles are said to be congruent if they have the same magnitude. AOB 45 degrees. DCF is also 45 degrees. That means angle AOB is congruent to angle DCF. Because they measure the same. They are different, two different angles. but they have the same measure, so they're congruent to each other. Two line segments are congruent. Two line segments are congruent if they're of the same length. Two angles are congruent if they have the same magnitude. Similarly, two circles are said to be congruent to each other if they are of the same radii. If the radius of the circle is equal to the radius of the circle, that means these two circles are congruent to each other. So congruent circles meaning circles having the same radii. Congruent circles meaning circles, two different circles, but they have the same radius. So here, prove that equal chords of congruent circles subtend equal angles at their centers. So we have congruent circles. Congruent circles. See here, there's one circle. We have another circle. And these two circles are congruent circles. That means they have the same radius. Prove that two equal chords of congruent circles. These are two congruent circles. We have equal chords. So chord AB is equal to chord CD. Chord AB is equal to chord CD. Equal chords of congruent circles. Subtend equal angles at their centers. So let the center here be O. Let the center here be O dash. So this is the angle made by AB at the center. This is the angle made by CD at the center. We'll have to prove that this is equal to this. They subtend equal angles at the center. We'll have to prove that this angle is equal to this angle. So congruency, prove that these two triangles are congruent. And why should OA be equal to O dash C? Because they are two congruent circles. So they have the same radius. They are two congruent circles. They'll have the same radius. OA is equal to O dash C. Radii of congruent circles. So the statement is prove that equal chords of congruent circles subtend equal angles at their centers. The proof is easy, children. Take a screenshot. Congruent circles are circles with the same radii. Prove that if chords of congruent circles subtend equal angles at their center, then the chords are equal. Converse. Here, prove that equal chords of congruent circles subtend equal angles at their centers. This is the converse. Prove that if chords of congruent circles subtend equal angles at their centers, then the chords are equal. In the first one, here chords are equal. You must prove that they subtend equal angles at their centers. Here, the chords are not given to be equal, but they make equal angles at their centers. Then you must prove that the chords are equal. So simple, the proof is simple, children. See, this is equal to this radii of congruent circles. Then this one is equal to this one. Again, same reason, radii of congruent circles. And then it's given that they subtend equal angles at the centers. So this angle is equal to this angle. So by SAS congruence criterion, these two triangles are congruent to each other. CP, CTC, you will have AB is equal to CD. AB is equal to CD, CP, CTC. Here you have these two. Take a picture, children. Exercise 10.2, this is. 10.1, we had true or false and fill in the blanks. This is exercise 10.2. We have only two proofs here. One statement and the other is the converse of the statement. This is the first one and this is the second one. The two circles are congruent circles. That is, they have the same radii. So in the two circles, if the chords are equal, you should prove that they subtend equal angles at the center. The converse is, if the two chords, they subtend equal angles at the center, then you should prove that the chords are equal. That is, if this angle, okay, the first one is, if AB is equal to CD is given to you. If AB is equal to CD, then you should prove that angle 1 is equal to angle 2. The converse is, if angle 1 is equal to angle 2, then prove that AB is equal to CD. This is what these two proofs are all about. So I told you exercise 10.1, true or false and fill in the blanks. Exercise 10.2, these two theorems. One is the theorem and the other is its converse. Should I show you again? This is the first one. Second one. Just read this, children. Read this one, children?
Yes, ma'am.
Yeah. Have a look at this. All right. So when we're given 1 point or 2 points, we see that we can draw as many circles as we wish, passing through 1 or 2 points. So when you have 1 point, you can draw many circles. I'm not good at drawing. I'll show you. Passing through you're given 1 point. Say you're given 1 point. 1 point P. So you can draw a circle like this passing through P. You can draw a circle like this passing through P. You can draw a circle like this passing through P. You can draw a circle like this passing through P. So you can draw so many circles, you know, you can draw infinitely many circles passing through the point P. Same is the case when you're given 2 points P and Q. Same is the case when you're given 2 points P and Q, you can draw as many circles as you want passing through these 2 points P and Q. See, that is, you know, you can just tell like this. So there can be a circle having the points P and Q here. There can be another circle having P and Q here, P and Q here like this. P and Q here like this. So see here, in this circle. The points P and Q are here. Oh my God. This circle, you can see the points P and Q here. This circle, with the points P and Q on the circumference like this. A bigger circle with the points P and Q on the circumference here. So when you're given 1 point or 2 points, you can draw as many circles passing through the single point or passing through 2 given points. If you're given 3 points. So when you're given 1 point, you can draw as many circles as you wish passing through that single point or passing through 1 point. Similarly, you can draw as many circles as you wish passing through 2 given points. What if you're given 3 points? 3 points. We're given 3 points like this. Now, when you have to deal with 3 points, 2 situations arise. Are the 3 points collinear or not collinear? Okay, when the 3 points are collinear, when the 3 points are not collinear. See it? When the 3 points are collinear, when the 3 points are not collinear. When we have to discuss about circles, a circle or circles that can be drawn passing through 3 points, we have 2 situations. When the 3 points are collinear, when the 3 points are not collinear. So the first case where the 3 points are collinear. Okay, so you have 3 points and the 3 points are collinear. That is, they lie on the same straight line. They can be connected by the same straight line. See, 1 point, we saw that when you're given 1 point, you can draw as many circles as you wish passing through that 1 point. Same thing holds good for 2 points. When you have 2 points, you can draw infinitely many circles passing through these 2 points or the 2 given points. 3 points, 2 cases. When the 3 points are collinear, when the 3 points are not collinear. When the 3 points are collinear, when the 3 points are not collinear. So this is the first case where the 3 points are collinear. So you will agree when I say that, you cannot draw one circle passing through all the 3 points. You can draw a circle passing, you cannot draw one circle passing through all these 3 points. When the 3 points are collinear, you will agree that you cannot draw one circle passing through all the 3 points. See, like if you can draw a circle passing through these 2 points, but this point will not pass through the circle, or this point will not lie on the circle. Or you can draw a circle passing through this point and this point. But this point will not, the circle will not pass through this point. Or you can draw a circle passing through these 2 points. These 2 points, then this will be left outside. So when the 3 points are collinear, you cannot draw one circle passing through all the 3 points. When the 3 points are collinear, you cannot draw, there is no one circle that can pass through all the 3 points. You see here, if you draw a circle, if you draw a circle like this, passing through these 2 points, then this point lies inside the circle. Then this point lies inside the circle. So see here, inside the circle. Or if you draw a circle passing through these 2 points, then this point lies outside the circle. So one of the points will remain either inside or outside the circle. One of the points will remain either inside or outside the circle. So when the 3 points are collinear, the heading is number of circles that can be drawn passing through 3 given points. When we have 3 points, case 1, when the 3 points are collinear, no circle can be drawn passing through all the 3 points. What happens? One of the points will lie either inside or outside the circle. Let me show you that again. So if you draw a circle passing through these 2 points, then this point lies outside the circle. If you draw a circle passing through these 2 points, then this point remains inside the circle. So one of the points will remain either inside or outside the circle. No circle can be drawn passing through all the 3 points when they are collinear. When the 3 points are collinear. Now when the 3 points are not collinear, so not collinear meaning they lie like this here. These 3 points are not collinear because see, you cannot connect them by the same straight line. No, they're not connected by the same straight line. You can see AB and BC. If you have to join these 3 points, they're not collinear, right? They're not collinear, meaning they cannot be connected. See here, ABC, they're collinear. ABC, they're collinear. So you are able to join all the 3 points by the same straight line. Here, the 2 points are sorry, not 2. Here, the 3 points are not collinear. So see here, you have 2 line segments, AB, BC. Like this, you can connect them, but you cannot connect them using the same straight line. Now, in this case, when the 3 points are not collinear, very important, when the 3 points are not collinear, there is one and only one circle that can be drawn passing through these 3 points. There is one and only one circle that can be drawn passing through these three non-collinear points. That is, there is a unique circle. There will be a unique circle passing through. Unique meaning there's only one circle, one and only one circle that can be drawn passing through three non-collinear points. There is one and only one circle that can be drawn passing through three non-collinear points. When the 3 points are collinear, you cannot draw a circle passing through all the 3 points. When the 3 points are collinear, you cannot draw one circle passing through all the 3 points. When the 3 points are not collinear, like here, when they're not collinear, like as you see here, you can see here, there's one and only one circle. You can see a circle passing through A, B, and C. There is one and only one circle, or there is a unique circle passing through three non-collinear points. Now, how do we draw that circle? How do we draw that circle passing through? How do we draw that unique circle passing through these 3 points A, B, and C? These three non-collinear points A, B, and C. Construct the perpendicular bisector of AB. So we know how to construct the perpendicular bisector like this. Construct the perpendicular bisector of AB. Construct the perpendicular bisector of BC. That 4-arc method. Let the perpendicular bisectors meet at O. Construct the perpendicular bisector of AB. That is, you'll have to put your compass at A and B and cut these. Let me show you. Compass. You'll have to keep the tip of the compass at A and B. Keep it at A, draw an arc, keep it at B, same radius, cut the earlier arc. Cut the earlier arcs. And you know the radius should be more than half of AB. It should not be too small, then the arcs will not intersect. The arcs will not intersect. With A and B as centers and radius more than half of AB, draw arcs on either sides of AB. And when you join, this is the perpendicular bisector. Similarly, with B and C as centers and radius more than half of BC, draw arcs on either sides of BC. So now, and join, of course, and join. So this is how you construct the perpendicular bisectors of the line segments AB and BC. Now let them intersect, let the perpendicular bisectors intersect at O. Now with OA or OB or OC as radius, all the three will measure the same. All the three will measure the same. You use the compass, use your compass and see here, you can see the perpendicular bisector. You can see the line segment AB here and its perpendicular bisector PQ here. You can see the line segment BC here and its perpendicular bisector RS here. You can see that the perpendicular bisectors PQ and RS intersect at O. Intersect at O. The perpendicular bisectors PQ and RS, they intersect at O. Now with OA or OB or OC, those 3 points A, B, C, OA, OB or OC as radius, that is, put your compass here and measure OA with the compass. Open the mouth of the compass. Open the mouth of the compass to measure OA or OB or OC. All the three will have the same measure. All the three will have the same measure. So with OS center and OA, OB or OC as radius, draw the circle. You will see that the circle will pass through A, B and C. And that's the only circle that can be drawn passing through A, B and C. Given 1 point, number of circles that can be drawn passing through a given point, infinitely many. Number of circles that can be drawn passing through 2 given points, infinitely many. Number of circles that can be drawn passing through 3 given points, we have 2 cases. When the 3 points are collinear, when the 3 points are not collinear. When they are collinear, you cannot draw one circle passing through all the 3 points. That means there is no circle. There is no circle. You cannot draw one circle. There is no circle that can be drawn passing through 3 points. When the points are collinear. When the points are not collinear, there is one and only one circle that can be drawn passing through these 3 non-collinear points. And how do we do it? How do we draw that circle? So simply take, if you have, simply take 3 points, X, Y, Z. Join X, Y. These are the 3 non-collinear points. X, Y, Z are the 3 non-collinear points. X, Y, and Z are the 3 non-collinear points. Join X, Y, join Y, Z. Construct the perpendicular bisector of X, Y. Construct the perpendicular bisector of Y, Z. Let them meet at O. Now with OX or OY or OZ as radius, draw a circle. Draw a circle. You will see that the circle will pass through the 3 points X, Y, and Z. So that's the theorem. There is one and only one circle. There is one and only, I forgot to type one. There is one and only one circle passing through 3 given non-collinear points. There is one and only one circle passing through 3 given non-collinear points. And that circle which we drew, so we know that when 3 points, just 2 more minutes, children, I'll wind up the session. How many of us are there? Class, use the emoji, raise your hand. Sangamitra, Nikita, Satvika, Arav, Kanishka. Sangamitra, Nikita, Satvika, Arav, Kanishka, Nivedita, Vasudevan, Tarun. Okay. All right, children. So when the 3 points are not collinear, when the 3 points are not collinear, they are joined to form a triangle. When the 3 points are not collinear, they can be joined to form a triangle. And that circle, that one circle which can be drawn passing through these 3 non-collinear points is called the circumcircle of the triangle. Circumcircle. That circumcircle is that circle which can be drawn passing through 3 non-collinear points. When we consider 3 non-collinear points, we know that when 3 points are collinear, no triangle is formed. We need 3 points to define a triangle. We need 3 points to define a triangle. But when the 3 points are collinear, no triangle is formed. When the 3 points are collinear, no triangle is formed. So we need 3 non-collinear points to make a triangle. We need 3 non-collinear points to make a triangle. You see, these 3 points are not collinear, so a triangle is formed. A triangle is formed. And what did we understand? When we have 3 non-collinear points, there is one and only one circle that can be drawn passing through these 3 non-collinear points. Okay, so when you join the points, you can form a triangle. And that circle is the circumcircle. And that circle is called the circumcircle. Its center is called the circumcenter. The center of the circumcircle is called the circumcenter. And the radius of the circumcircle is called the circumradius. Circumcircle, circumcenter, circumradius. Like we say center, circumcenter. Radius, circumradius. And the circle is called the circumcircle. Take a screenshot, children. There is one and only one circle that can be drawn passing through 3 non-collinear points. All right, children. All right, children. So that's it for today's session. Thank you so much. You may leave the call. Good night.
Thank you, ma'am.
Thank you, children. Good night.